Today, I'm going to answer a question from a patron by the name of Joseph Griscavage. How'd I do? And first of all, a big thank you, Joseph, for your support. You really are making this possible. And the question is, can you explain an astable multivibrator? I think I can do that. But before I do, I need to go into more detail about charging and discharging capacitors than I have in the past. If you think you don't need that, you might want to skip ahead to around here where I start talking about astable multivibrators themselves. Or if you want to go to the practical transistor circuit, you might want to skip to around here. And you can look in the description below for links to skip to those points. And let's take a look at my demonstration circuit and just look at capacitor charging and discharging and take it to another level and get ready to explain an astable multivibrator. So we're going to start out with a battery and a switch. Let's make that a 10-volt battery. This is going to go to a 1 ohm resistor and a 1 farad capacitor. And I'm going to put another switch right here just so I can discharge that capacitor. So 1 farad, 1 ohm, 10 volts. Now I'm going to close this switch and leave it closed for a few seconds just to make sure that any energy in that capacitor has been discharged and it has 0 volts across it. Now, let's open that switch and see what happens when we close this switch. When that happens, what does the capacitor look like? At the moment that switch closes, the capacitor looks like what? It looks like a short circuit. So what we have is energy flowing into this side of the capacitor, and so electricity is flowing there and piling up, and that is pushing electricity off the other side. Now, of course, what is happening is we have electrons flowing from the negative side of the battery, and they're piling up on this side of the capacitor, which of course is 2 plates of metal separated by an insulator. The electrons can't cross that insulation, but they can influence electrons on the other side and push on them, and it pushes electrons off. So every electron that piles up here pushes off another electron on the other side. But we talk about conventional current in this class. Most of academia does, the electronics industry does, so we're going to talk about conventional current. So our current's going to go from positive to negative, and just know that we have current piling up here and it's pushing current off the other side. So even though this is an insulator and no electricity can pass through it, for every coulomb of charge that piles up here, another coulomb leaves, so an amp in equals an amp out. Sure looks like a short circuit to me. So at the moment I've flipped that switch, our capacitor looks like a short circuit. So a discharged capacitor appears to be a short circuit. So let's put the capacitor back there and see what happens over time. With 1 ohm and 1 farad, we have a time constant of 1 second. R times C equals our time constant. 1 times 1 equals 1. What that tells us is it's going to take 1 second for this to charge up to 63.2% of this voltage. So after 1 second, this is going to charge up. If we put a voltmeter across it, we will see 6.32 volts after 1 second. And after about 5 seconds, we're going to see 9.95 volts there. Yours makes no difference. This has reached 10 volts after 5 seconds. So after 5 seconds, this looks like exactly what it is, a insulator. 2 conductors separated by an insulator. We have 10 volts worth of charge piled up on this side and pushed off the other side, so there's a 10 volt difference. I see a 10 volt difference with my voltmeter. Remember, your voltmeter has a black and a red lead. Here they are, and it tells you the difference in voltage between the two. And if the red lead's at a higher voltage, it gives you a positive reading. Red lead's at a lower voltage than the black lead, it's a negative reading. We'll be reiterating that as we go along. So after a while, what we have is 10 volts here, 10 volts there. The battery is pushing with 10 volts this way. The capacitor is pushing with 10 volts that way. It's like filling up an air tank. I have a compressor that gives me 100 pounds per square inch. I push some air into an air tank, it starts to fill up. At first the air goes in real easy because there's nothing pushing back, but as that fills up I get more and more pressure pushing back, and eventually I have 100 pounds in the tank, 100 pounds in the compressor. The tank's pushing back just as hard as the compressor's pushing in, and I get no flow through there. Same thing happens with the capacitor. I'm pushing in with 10 volts. It's not pushing back, so plenty of current goes through. But as that charges up, I get more and more push back. And eventually when this reaches 10 volts, and that's 10 volts, they're pushing back with the same energy, and I get no flow. So at that point, it just looks like an open circuit. So now it looks like that. And I see 10 volts across it. There's no current flow, no current flowing through this resistor, so there's no longer any voltage drop across it. So I have 10 volts here, 10 volts there. Let's put a meter on here to look at our voltages. So there's my black probe down there. So as soon as I put my black probe there, that defines that as 0 volts. I have 10 volts higher up here. It's a 10 volt battery, 0 volts, 10 volts higher there, so that's going to be plus 10 volts. There's no voltage loss across here because there's no current flowing through there. To get a voltage difference, I need either a voltage source, which we'll talk about in a second, or current flow through resistance. I have resistance, but no current flow, so no voltage difference. So I have 10 volts here, 10 volts, just 10 volts there. And of course, 0 volts down here, and the capacitor is fully charged. And there's my circuit. So what's going to happen when I open this? Nothing's going to change. Still have my charged capacitor. So now let's go ahead and flip this and see what happens. So now I have a current path going this way, and this capacitor is basically acting like a battery. Now, of course, it doesn't have the energy store a battery has in the form of chemistry. So it discharges pretty quickly. It doesn't have a whole lot of energy in it. But the moment I flip this switch, that pretty much looks like a 10 volt battery. Let's reduce our clutter here. So I've opened that switch. I've disconnected this part of the circuit. And now I have current flowing in that direction because this looks like a 10 volt battery. And it's going to discharge. Let's look at the voltages across there as this goes on. I'm going to put my red lead here and let that completely discharge, and then we'll go through the cycle again. So let's open that up, and we're ready to go through the cycle. So it's completely discharged. There are 0 volts across this capacitor. So what's it look like? A short circuit. Let's make it a capacitor again because I don't want to get confused here. So 0 volts looks like a short circuit. That's open. So what voltage do I see everywhere? I see 0 volts, 0 volts, 0 volts, 0 volts everywhere. The only place I see anything else is 10 volts here because that's the other side of the battery. So 0 volts, 10 volts higher. The switch is open, so everything else over here is 0 volts. I close that switch. It begins to charge. After 1 second, I'm going to have 6.32 volts here. I have current flowing through this resistor, so I have a voltage difference. I have 10 volts here, 6.32 volts here. But as time goes by, after 5 seconds, this has reached 10 volts. There's no longer a voltage difference. There's no longer current flow. And so I have basically 10 volts everywhere up here. And if I put my probe down here anywhere, of course, I'm going to see 0 volts. So now, if I open this up, what's going to happen? Of course, not much of anything. I'm still going to have the same voltages anywhere. This capacitor is just going to be sitting there. It looks like a battery, but doesn't have as much energy. So I have 0 volts, 10 volts, 10 volts. Not much exciting happening there. But what's going to happen when I close this switch? Well, now that shorts down to there. This is going to become 0 volts because what do I have? I have 0 volts here, a short circuit, so there's 0 volts there, so they're going to be the same voltage. I may have current flowing through there, but no resistance, therefore no voltage drop. So 0 volts, same voltage there, 0 volts. This is 10 volts. All my current's flowing through that resistor. But as this capacitor discharges, that voltage goes down. After 1 second, it's going to be 3.68 volts. And after 5 seconds, it'll be down to 0 volts. So there we have it. Not too complicated. I open this switch and close that switch. The capacitor charges up and this voltage goes up to 10 volts. I open that switch and close that switch. The capacitor discharges and that drops down back to 0 volts. So charge, it goes from 0 to 10. Discharge, it goes from 10 to 0. Not too exciting at this point. I'm going to make a slight change in the circuit, get rid of my switch there, and replace it with a resistor. Now what's going to happen when I close this switch? Well, I have 10 volts here, 1 ohm, and my capacitor. It's going to be just like it was before. So it's going to start charging, and after 1 second it'll reach 6.32 volts. Let's put our meter here, 6.32 volts after 1 second, and after 10 seconds it's going to reach about 10 volts. So same as before, but what's going to happen when I open that switch? Now I've disconnected the voltage source. Now let's take a careful look at what's happening over here. I now have a 10 volt source over here. It looks like a 10 volt battery. And I have two 1 ohm resistors in series. So I have a circuit and it's going to start discharging. And I have 2 ohms instead of 1 ohm. So it's going to take twice as long to discharge as it did to charge. So it's going to take 2 seconds to get down to 3.68 volts. And then it's going to take 10 seconds to get all the way down to 0 volts. But I have a convenient circuit here now where I can close the switch and it charges, and open the switch and it discharges by itself. So close it, it charges, so I watch my voltage goes up to 10 volts, takes 5 seconds, open the switch and it discharges and takes 10 seconds to get down to 0. And of course I need to make this back into a capacitor instead of a battery. So far nothing remarkable is happening. This just goes up to 10, down to 0, up to 10, down to 0. It's just taking 5 seconds to get to 10 volts and 10 seconds to get back down to 0 volts. Now let's redraw the circuit again. Take us one step closer to the Astable Multivibrator. What I'm going to do now is simply move the switch down to here. Leave our resistor here. Okay, now what's going to happen when I close this switch? Well, it's the same circuit. It doesn't matter where I put the switch. I still have the current flowing in, so it's going to be 10 volts here. It's going to be charging that capacitor, and after 1 second it's going to reach 6.32 volts. After 5 seconds it's going to reach 10 volts. It's going to stop charging, and so we're the same place we were before. So let me go ahead and put my black lead down here. And we know we're going to read plus 10 volts there because it's the other side of that battery. After 5 seconds this is completely charged, so that's going to be 10 volts here. And now let's see what happens when we open this switch. Okay, follow closely. This is going to look a little weird. So what we have now is we've disconnected the battery, so without the loop we don't have any more current flowing in. So this is going to start acting like a battery. So it looks like a 10 volt battery. And how is the current flowing? It's going to flow through this resistor. Can it flow that way? Nope, there's no connection. So there's only one possible current path. So I have a series circuit flowing through those two resistors. Looks pretty much the same as before, but let's watch what happens to our voltages. I want to look at what the voltage at this point is here. So I'm going to redraw this circuit for a moment. Make sure we follow it. There's our charged capacitor looking like a battery. And for the moment I'm going to disconnect that. So what do we have? A standard series circuit. 10 volts, two 1 ohm resistors. And if you are not familiar with series circuits and Kirchhoff's voltage law and all the things we're going to talk about here, such as especially voltage dividers, be sure you read the lessons on voltage dividers, Kirchhoff's voltage law, and series circuits. Make sure you understand them, or this may become very confusing. But what we have is one possible current path, so there's a series circuit. And what are the voltages going to be at the different places in the circuit? First of all, this is no longer doing anything because they're disconnected. So let's connect our black lead here. So that is our new 0 volts. So if I put my red lead here, I get 0 volts. What am I going to get here? 10 volts, because it's like a 10 volt battery. 0 volts, 10 volts higher, plus 10 volts. But we have our current flowing through. So what's the voltage going to be right there? Well, it's a series circuit, so the current is the same everywhere. And if the resistors are equal, they must have equal voltage. So that has the same voltage as that one, and they must add up to our source voltage. So this voltage and this voltage must add up to 10 volts. Therefore, I have 5 volts and 5 volts. So if I have 0 volts here, and I have 5 volts there, and the current's flowing this way, so the voltage is higher here than lower there. So 0 volts, 5 volts higher, that means this must be 5 volts. And this is going to be 5 volts higher than that. So it's going to be plus 10 volts. Okay, because as soon as I connect this over, it's going to get weird. So let's take that off and connect this over. And what's going to happen to all of our voltages? First of all, compared to here, it's still going to be 10 volts higher, 10 volts, 5 volts, 0 volts. But we're not measuring with our black lead here. Our black lead is now over here. So what are we going to measure with our black lead over here? This is 10 volts higher than that because there's a 10 volt battery. And this is going to be 10 volts, right? And what did we determine? The voltage here must be 5 volts higher than the voltage here. So that has to be plus 15 volts. So that's what's happened to our circuit. Now we have 10 volts, 15 volts. What's the voltage here? Remember, we determined that this voltage must be 5 volts lower than that voltage. So this voltage is going to be plus 5 volts. So whatever voltage this is, that one must be 5 volts lower. Whatever voltage this is, that one must be 5 volts higher. So 10 volts, 15, 5. And just to make sure you understand, because they might be going, what the heck? Let's disconnect that. Okay, and put our black lead back here. So measuring from this as our 0. There's our 0 volts. This is going to be 0 volts. That's going to be plus 5. That's going to be plus 10. So once again, this is 5 volts higher than that. This is 5 volts higher than that. Remember that voltage is relative. I'm trying to emphasize this because this can be confusing. But voltage is relative. We're always comparing one voltage to another. So if we take this away and ignore that for a moment, we don't know what these voltages are. But we do know that this is 5 volts higher than that. This is 5 volts higher than that. And there's a total of 10 volts between here and here. Now, as soon as we connect this up, what happens? Now we have a good solid, this is 10 volts. There's our negative lead down here now, 0 volts plus 10. We know that must be 5 volts higher. We know this must be 5 volts lower. And a 10 volt difference here. But that means that, of course, if this is plus 5 and that's 10 volts higher, once again, we're at. So, when we open that switch, when it's closed and everything is charging, this gets up to 10 volts. But when we open that switch, suddenly this jumps up to plus 5 volts. We close the switch, that goes to 0 volts. We open the switch, that goes up to plus 5 volts. And what happens to the capacitor? Well, let's make it back into a capacitor. And as we leave this switch open, that capacitor is going to discharge through these two resistors. So it's going to take 2 seconds for it to reach 3.68 volts. So it starts at 10, drops down by 63.2%, gets down to 3.62 volts after 2 seconds. So these voltages drop. So the difference will be 3.62 volts. And then eventually, I don't want to do the numbers, I think it's going to get too confusing, but it's going to drop down to 0 volts. after 10 seconds. So what has happened? We have a difference of 0 volts between there and there. Is there any current flowing? No. So is there any voltage differences? So what's happened is, yeah, this is getting weird, isn't it? This is 10 volts, that's 10 volts. Now, there's no current flowing. So is this voltage going to be higher? No, no current flowing. No current flowing, no voltage difference. So the 10 volts here, it's going to be 10 volts there. Is there any current flowing through here? No. So with no current flowing, no voltage difference, so 10 volts here we have. And so everywhere we look, so basically all we have now is just some circuit with no voltages attached to 10 volts. So it's 10 volts, 10 volts, 10 volts, 10 volts, 10 volts everywhere. So what happened? When we opened the switch, when the switch was closed, this was 0 volts. When we opened the switch, it jumped to plus 5 volts and then went higher and higher and higher, goes up, 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 and eventually reaches 10 volts. So what's happening on this side of the capacitor is when we start the charging, this goes to 0 volts. When we open that up, it jumps to 5 and then climbs up to 10. Close the switch, that drops down to 0. This charges, goes up to 10 volts. Then we open the switch, this jumps back up to 5, and then goes up, 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 up to 10. So we've got a weird thing going on there. Let's just draw it back the way we had it before. So there's our circuit. We close the switch. And at that moment, we have 0 volts, 0 volts, 10 volts. This charges. After 10 seconds, this becomes 10 volts. It's 10 volts everywhere up here, 10 volts, everywhere down here, 0 volts. When we open that up, what happens? This voltage jumps up to 5 volts. That jumps up to 15 volts. And then as that capacitor discharges, this voltage goes up towards 10. This voltage drops down towards 10. And after 10 seconds, because it's got 2 resistors to go through, the voltage difference across this capacitor becomes 0. No difference. So the voltage is the same on this side and that side. So this voltage dropped from 15 down to 10. This went from plus 5 up to 10, and so everything is 10 volts everywhere. So close the switch, down to 0, open the switch, up to 5, climbs up to 10. Switch open, close the switch, this drops down to 0 volts, climbs up to 10, open the switch, jumps up to 15, and drops back down to 10. So now let's make the next step going to the Astable Multivibrator. Let's draw it a little smaller because I need more stuff on the board. So there's our battery. There's our resistor and capacitor. Back to our switch. Back to the battery, that 10 volts. And there's the switch open, and of course our other resistor. So what's it going to do? We close the switch, this is going to charge up, and when we open the switch, that's going to jump to 15 volts, that'll jump to plus 5, and that'll drop down to 0, that'll go up to 5 when that reaches 0. Now, what we could do is make an oscillator if we had some way of when this hit 10 volts, if we could trigger that to open and cause it to discharge. So let's make another circuit that looks just the same. I'll draw it over here. I'm going to draw a mirror image of the circuit here. Let's see how well I can do this. And what I'm going to do is have this circuit connect over to this circuit. I'm going to put a relay right here. So what am I drawing here? I'm going to put a ground symbol there. I don't want them connecting together yet. So I'll just put a ground symbol, which means I'm going to connect over to here. There's our ground ground number 1. I have a separate ground over here. So here's an identical circuit, and this is a relay. I normally draw a relay like this. There's my contacts, and so what we have is an electromagnet. I ground this one. Let's put 10 volts here. That's going to make a magnetic field, pull this armature down and close the switch. We take the 10 volts away, the magnetic field goes away, and the armature opens up, so it's an electromagnetic switch. And I'm just drawing it differently. So there's the relay coil. When I have 10 volts go to this, it closes that switch. When I take the 10 volts away, that switch opens. So now I'm making a circuit where when this hits 10 volts, it's going to start this side charging. Okay, so let's close our switch here. And this is going to start charging up, charging up, charging up. And when this reaches 10 volts, it's going to energize this relay. And that's going to close this up. And now this is going to start charging. And after 1 second, this is going to get to 6.32 volts. After 10 seconds, it's going to get to 10 volts. And charge just like that. Okay. So I got this to charge, triggered this one, and 5 seconds later, this one was charged. Wouldn't it be cool if I can make this now operate that relay so that when this gets charged, it opens that relay and causes this one to discharge. So let's just cross-couple those like this. Let's get their voltages out of the way here. I'm going to draw my grounds separately. I have 2 separate batteries here, but I really won't in the end, but I'm just drawing it that way. So there's our mirror image circuits. Now, I've got a problem here. How do I get this whole thing started? So what I'm going to do, this is going to be open. And so this one's going to be open too, right? Okay, somehow I've got to get this thing started. So what I'm going to do is I'm going to just take my finger and hold this down over here to get the whole circuit started. So what's going to happen now, this is all discharged down to 0 volts, 0 volts. But if I put that down, what's going to happen, this is going to start charging to 10 volts. So that's going to go up and up and up. And when this reaches 10 volts, what's going to happen? That reaches 10 volts. That's going to energize this relay, and it's going to start this circuit charging. So now I'm going to let go. I let go of that. Now watch what happens. As soon as I let go of that, this jumps up to plus 15 volts. And this jumps up to plus 5 volts. And as time goes by, this drops down to 10 volts. This goes up to 10 volts. So this is going to stay at 10 volts and keep that charging. So this is going to keep on charging as these 2 voltages change. So now this is plus 10, and that's plus 10. So now this capacitor is discharged, but this one is charging. And so as time goes by, this eventually reaches plus 10 volts. Okay, here we are. This is open because that's unenergized. That has not reached 10 volts yet. This is discharged, so there's no voltage across here. 10 volts everywhere. This is still 10 volts. Now, as soon as that reaches 10 volts, what's going to happen? It's going to trigger this relay to drop that switch. Now that switch is on. What's that going to do? It's going to pull this voltage down to 0 volts. How much voltage is across this capacitor? It's discharged. So it's going to pull that voltage down to 0 volts. And what's that going to do? It's going to pop this open. So when that pops open, this is going to jump up to 15 volts. This is going to jump up to plus 5 volts. That's going to discharge, but this remains at above 10 volts. So now this is charging up. After 1 second, that's going to reach 6.32 volts. It's going to eventually reach 10 volts. In the meantime, this has gotten down to 10 volts. 10 volts. Remember, that's going to drop down from 15 down to 10. This is going to be plus 5 up to 10. So that's going to discharge. That's down to 10 volts, still holding this closed. But when this charges up, charges up, charges up, that's going to reach plus 10 volts. What's it going to do? It's going to energize this relay, pull that guy right down. What's going to happen? It's going to pull that down to 0. How much voltage was across this? No voltage. It's going to pull that down to 0. That's going to open this switch. Okay, as soon as that switch opens, that jumps up to 15 volts. This jumps up to 5 volts. Now that 15 is dropping down towards 10. This 5 is climbing up towards 10. Eventually this reaches 10 volts. 10 volts, no voltage across the capacitor. What's this doing? That's 0 volts. This is charging, going up, 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 and it reaches 10 volts. What's it going to do? It's going to close this switch. Boom. That's going to pull this down to 0 volts. How much voltage is across the capacitor? None. So it's going to pull this down to 0 volts. And the capacitor starts charging. But as soon as that hits 0 volts, what happens? That opens. How long do I need to keep this up? That opens. This jumps up to plus 15, plus 5. So that's slowly dropping down towards 10. This is slowly climbing up towards 10. But this is now charging. When this reaches 10, what happens? Pulls that switch down. This suddenly goes to 0. That goes to 0. Pops that open. 15. 5, and it just keeps going back and forth and back and forth. I don't want to keep repeating that, so if you want to follow the cycle again, just back it up and follow what happens. First, this one charges and triggers this one. Then that one charges and triggers that one. One charges, then the other charges. One charges, then the other charges. And what I've just done is made an astable multivibrator with relays instead of transistors. Now let's redraw this circuit and get a little closer to what we're used to seeing with an astable multivibrator. So I'm going to get a little closer to the way we're used to seeing an astable multivibrator. I'm still going to do this using relays. So there's our circuit, the same exact circuit. And this is the resistor that, let me draw it over here just to make sure we're understanding what's going on here. So here's our 10 volts, that means the positive side of the battery. There's that resistor. There's that capacitor. And there's our switch. I just need to put the other resistor in right here. So the other resistor goes from the battery. There it is. And which side of the capacitor does it go to? It goes to the opposite side of the capacitor. So there's the same exact circuit. So let's go ahead and follow how this goes for a second. So I close the switch, and this capacitor starts to charge. And goes up. Eventually, this capacitor reaches 10 volts. And this is going to be 0 volts because that's going to ground. Now when I open the switch, what's going to happen? This is going to suddenly jump up to plus 15 volts. That's going to jump up to plus 5. This is going to slowly drop down. This is going to discharge. Now, how's it going to discharge? Well, remember, this is just telling me these are connected to the same place. So what I have is, I'm just saying those three places are connected together. So how's it discharging? It's discharging that way. Let's put that back together. So this is discharging that way. I'm just connected both to the same place. So it's discharging like that. That is just connected to the battery. So it's discharging, discharging. That goes up to 15 volts like we showed before. That goes to plus 5. And then this drops down to 10. This goes up to 10. So that jumps up to 15 and then it discharges down to discharges down to 10. This goes to plus 5 and discharges up to 10. And eventually it follows the same pattern. So it's the same circuit. We can charge it by closing the switch, discharge it by opening the switch. So they're the same exact circuit. And we'll draw the other side over here. They're connected to the same battery. I'll just draw a mirror image. I'm drawing this a little differently, and of course I'm using relays again. So there's the same exact circuit. Now we take top of this, run it over to our relay. Take the top of this, run it over to that relay. So like before, I'll give it some help by closing that and holding that with my finger. That charges up, charges up, charges up. When it reaches plus 10 volts, that's going to close this relay. I'm going to let go of this one. Now we've got the cycle started. So that closes that relay. That means this is going to now start charging. Okay, when that opened up, don't forget this went to plus 15 volts. And that went to plus 5. So as that climbs up in voltage, it reaches 10 eventually. This goes down in voltage, it reaches 10. At the same time this is charging, when that reaches plus 10 volts, that's going to, let's get that out of the way there, reaches plus 10 volts, that's going to trigger this one. By that time this is at plus 10 volts, that's at plus 10 volts. They're the same voltage, so there's no voltage across the capacitor. So as soon as I flip that switch, that pulls that down to 0, which of course pulls that down to 0, which opens up this side. Now this starts to charge, and this of course goes to plus 15. That goes to plus 5. That slowly comes down to 10 volts. That slowly goes up to 10 volts. So there's no voltage across the capacitor. At the same time, this is charging, going up and up and up and up. This reaches plus 10 volts. It pulls this relay closed. That pulls this voltage down to 0. To 0. That opens this relay. Causes that to jump up to plus 15, plus 5. This drops down slowly towards 10. That slowly goes up towards 10. Now there's no voltage across that capacitor. At the same time, of course, this was climbing up and up and up, reaches 10 volts. Pulls this over, pulls the voltage down, opens this one back up, and we have the same exact thing going back and forth. So one side charges, triggers this relay, the other side charges, triggers this relay, and keeps going back and forth just like I demonstrated. I just drew the circuit a little differently. Now I'm going to redraw this just a little differently to make it look more like the traditional Astable Multivibrator. It's the same exact circuit. I'm just drawing it a little differently. Don't forget we have plus 10 volts over here. Let's look at the two. They're exactly the same circuit. All I did was just kind of rotate it around a little bit. Just kind of rotated it around. So instead of coming straight down and coming straight down to our capacitor, we're coming down into the capacitor and then down to ground. And this one's coming to the other side, so it's to the side of the switch. So these are exactly the same circuit. This is just the way we traditionally draw an Astable Multivibrator. So I'm going to do the same thing to this side. So there is our exactly the same circuit. So let's go through the cycle again. Let's open that up. They're both open. So I'm going to push this closed, get the whole thing started. As that starts to charge up, eventually it's going to be charging through this resistor here. So it charges up. Eventually this gets to plus 10 volts. When it does, of course, it closes this relay. At that point, I let go of this relay, and this starts to charge. Current flows this way, starts to charge that. And when this relay opened, what happened? This jumped up to plus 5 volts. That jumped up to plus 15 volts. This voltage slowly drops down towards 10. This voltage slowly climbs up towards 10. At the same time, this is now charging. Current's flowing this direction. When this reaches 10 volts, that energizes this relay, closes that. What's that do? It pulls this voltage down to 0. There's no difference in the two voltages. They were both 10 volts, and this was pulled down to 0. That puts 0 volts here and pops open that. Now this jumps up to plus 15, plus 5. This voltage is slowly going up towards 10. This voltage is slowly going down towards plus 10. At the same time this is charging, current's flowing in this direction. This charges up when it reaches plus 10 volts. It pulls that relay closed. That pulls these voltages down to 0. 0 volts pops that relay open. So we have the same thing happening over and over again. So there is your Astable multivibrator. I made it with relays because I think we can explain it better that way. We can visualize what's going on better with relays than we can with transistors. And as soon as I draw the transistors in here, it takes that visualization away, so it makes it a little hard to follow. So, yeah, it gets a little complicated and you have to follow some things in some unintuitive ways, but that's how an Astable multivibrator works. And once again, I'm going to redraw this. Just replace the relays with transistors, because that's what a transistor acts like. Now we've lost the visual cue of the switches, and that might be the reason you have trouble following an Astable multivibrator in the first place. So this is a little more difficult to visualize because we don't have the mechanical switches and the relays to help us visualize what's happening. And this is not normally part of your Astable multivibrator, but I'm going to put some resistors in here to isolate the bases of the transistors from these points here, because it'll act more like it did with the relay circuit. So I'm increasing the impedance of the base to emitter junction to make this work more like the other circuit. So let's explain that. First of all, when we turn the power on, both these transistors are going to try to turn each other on and turn each other off at the same time. It's going to be kind of a mess. But what's going to happen, because the two transistors are not equal, the capacitors and resistors are not equal, eventually one's going to turn on and the other one's going to turn off, and the cycle will start. So let's say this transistor turned on. So what do we have? That means we're going to have a closed switch here. So what's the voltage here? 0 volts. Closed switch, it's a short circuit. Basically, we have 0 volts here. Now it's a transistor. We're going to have something like 0.4 of a volt, but let's just ignore the saturation voltages and all the complications and just assume that looks like a closed switch. We can do that. So this is going to be essentially 0 volts there. And this capacitor is going to start charging towards 10 volts. And of course, this one is open, so there's no connection here. There's no current flow. That's going to be 10 volts. And this is going to be plus 10 volts because we have that resistor in the way in increasing our impedance. So this is turning that transistor on. This transistor's off. That's 0 volts. But it's charging through that resistor. So as it charges, it charges, it charges. Let's say when this reaches 10 volts, we get enough to get us at 0.7 volts here to turn on that transistor. So this transistor will turn on when this reaches 10 volts. So that transistor now turns on. So what's going to happen? It's 10 volts here, 10 volts there. There's no voltage across that capacitor. This shorts to 0, so that's going to pull this down to 0 volts. There's no voltage across the capacitor. That's going to pull that down to 0 volts, which means we get 0 volts here. This transistor is going to turn off. What happens now? This is going to jump up to plus 5 volts. This is going to jump up to 15 volts, just like before. That's going to hold this transistor on. Now what's going to happen is this current's going to be flowing this direction, charging this capacitor. That's going to go up and up and up. Eventually it's going to reach 10 volts. When it reaches 10 volts, it's going to turn on this transistor, so that transistor turns on. That's going to pull this voltage, which had climbed up. Remember, this is going to drop from 15 down to 10. So it's not on yet. This is going to go from plus 5 up to 10. So there's 10 volts here and 10 volts there. And when this reaches 10 volts, it turns on this transistor. That's going to pull this down to 0, which pulls this one down to 0 with it because there's no voltage across there. So that suddenly goes to 0 volts. That forces this transistor off. So that one's off. What's going to happen? It goes up to plus 5, plus 15, and now that capacitor is charging that direction. This is slowly going down to 10. This climbs up to 10. Eventually it reaches 10 volts. At the same time, this capacitor is charging, so it goes up to, eventually up to charging, reaches 10 volts. Now that turns this transistor on, pulls this down to 0, pulls that one down to 0 with it because there's no voltage across there. Down to 0 volts, turns that transistor off. Once again, that pops up to plus 5, pops up to plus 15. That discharges down towards 10, that discharges up towards 5. This is charging up, and then it turns it on, and they swap. So it just goes back and forth, just like with the relay. The only difference is these resistors won't be there. So now we have these capacitors going straight to the base of a bipolar junction transistor. And if you don't understand those, you might want to read the reading material or watch the video on how transistors work. And I have them linked below and up there. But I'll explain in such a way that maybe if you don't already understand them, you can still understand how the circuit's going to work. So now we have a problem in that the nature of the base to emitter junction of this transistor is basically a diode. So I'll draw a diode in here. And the diode has characteristics such that if you pass more current through it, it lowers its resistance, if you will. It may not be the most traditional way to explain it, but that's practically how it works. So I push more current through, it lowers its resistance such that the voltage across it, when the current is flowing in that direction, with the anode at the higher voltage and the cathode at the lower voltage, positive to negative, the voltage here can only get up to about 0.7 volts. Really, it can get a little higher. Small transistors can get to around 0.8 volts. Bigger transistors can get even higher. But your typical small transistor, about 0.8 volts. We're going to say 0.7 because that's the typical number that's thrown around. So that base cannot get higher than 0.7 volts. Make that positive, remind us that it's above ground. So that's going to pull this voltage here down to 0.7 volts. Let's get rid of these other numbers here before we get the situation even more confused than we want to. Okay, so that's the highest I can get. And there's going to be the same over here. So let's look at the circuit and how it works, knowing that. So let's assume that we're in a state where this transistor is on and this transistor is off. So this is going to be 0 volts because this is a closed switch. So just think of that as a closed switch over here. So short circuit to ground. In reality, because of the nature of the transistor, it's going to be a few tenths of a volt higher, but we're going to ignore that at this point. So that's at 0 volts. This capacitor is charging just like normal. So this voltage is rising. Before we talk more about that, let's go over here for a second because this transistor is on. Let's draw our arrow again. This transistor is on, so current is flowing this way from the base to the emitter. So no matter what the current is, within reason, it's going to be around 0.7 of a volt. Don't want to get too off base with what's really happening there, but we're going to know that this is going to be a maximum of 0.7 of a volt here, which means that's going to be the same story here. And over here, with the relays, when this turned off, this jumped up to 5 volts, and then as this capacitor discharged, that climbed up to 10. And this jumped up to 15 volts, and then as the capacitor discharged, that dropped down to 10. But this never can get above 0.7 volts. So at one point just before this turned off, this was 0 volts, that was 0.7 volts. And when I turn this off, let's just disconnect it to show that that transistor is off. This voltage really can't rise because that one can't rise either. This would like to jump up in voltage, but it can't because it's being held down by this transistor over here. So that's not really going to go up immediately like it did before. But of course this capacitor is going to be charging, current's going to be flowing in this direction. Before we had it discharging like that, current was flowing basically around like this. Well, the current's still flowing the same direction, so it's going to charge this side of the capacitor. That's going to climb up and eventually reach 10 volts. Just like before. Let's get rid of that clutter. It looks terrible there. So nothing really special, except this cannot get up to 10 volts. It's going to be held at 0.7 volts. Okay, so what's that going to do when we turn on this transistor? So right now we have 10 volts here and 7 volts there. Remember, this is acting like a battery now, so let's make it into a battery. Make sure we understand what's going on here. And what's the voltage across that battery? 10 volts here, 0.7 volts there. It's a 9.3 volt battery. Positive to negative. Look at it carefully. This voltage is 9.3 volts higher than that voltage, just like any battery. This voltage is 9.3 volts lower than that voltage. Remember, your voltage is always comparing one to another. So we have our black lead down here. That's our 0 volts. We see 0.7 volts here, 0.7 volts there, 10 volts there, 9.3 volt difference. So if we put our meter across there, we would read 9.3 volts. This voltage lower, that voltage higher. Can't emphasize that enough because something really weird is going to happen when I close this switch. Okay, so this voltage is going up, and eventually it's going to reach approximately 0.7 volts. That is going to, of course, be going to the base of this transistor, and when we put that 0.7 volts here, it's going to turn on, so it's going to become a closed switch. So let's close that down to remind us that this is now a closed switch. What's that going to do? That's going to pull this voltage down to 0, just like before. Now we have a 9.3 volt battery here, positive to negative. So what's going to happen if I have a 9.3 volt battery? I'll just draw it over here. And I'm going to see, let's see, where is my black lead of my meter? How am I measuring this voltage? Well, I've got 0 volts here. And of course that means I have 0 volts here. That's a switch, it's a short circuit. So I have 0 volts there. So basically my black lead is connected there. It's really connected here, but it's the same place because they're all 0 volts. So where is that on the battery? That's going to be the positive side. So my black lead is right there on my battery. So when I put my red lead here, what is it going to read? The black lead is at a higher voltage than my red lead. So by design, my meter is going to tell me it's a negative voltage. How much lower is it? 9.3 volts. So when I put my red lead here, it's going to tell me I have negative 9.3 volts. Is that right? Sure. I have 0 volts here. My black lead's at the higher voltage, my red lead's at the lower voltage, so I get a negative voltage. So 0 volts, negative 9.3. So I just closed that switch. Let's get that out of the way there. I have 0 volts here. I have 9.3 volts there. It's acting like a battery. So I have my positive at the 0 volts, my negative over here. So when I put my lead here, it's going to be 0 volts here. This is going to be 9.3 volts lower. So that's actually going to go to negative 9.3 volts. Is that something really spooky and weird? No, it's just I have 9.3 volts across a capacitor, but the higher voltage at 0 volts, the lower voltage is going to be whatever that capacitor voltage is. So 9.3 volts across the capacitor, higher voltage, lower voltage, that's going to be minus 9.3 volts. Did I get a voltage reversal? Remember, negative voltage is not the opposite of positive voltage. It's just a voltage that's lower than some other voltage I've called 0. What do we call 0? Wherever we put the black lead. So the black lead is here. Consequently, it's at the same voltage as we have here. So there's my black lead. I have a 9 volt battery, positive to negative. It's going to be negative 9.3 volts. So at the moment this transistor turns on, I'm going to, I'll just do it in black here, I'm going to get minus 9.3 volts at the base of that transistor. So you'll be reading about that negative voltage being presented to the transistors, and it sounds like, how could that happen? It happened because I have a 9.3 volt battery. I put the positive at 0 volts. The other side is going to be lower, negative 9.3. Nothing spectacular at all. It's just the way voltages work. So that is why we get a negative voltage at the base of our transistor when the opposite transistor turns on. So what's going to happen now? Well, this is going to reverse bias the base to emitter junction of that transistor. So now if we look at the diode, it's going to be a higher voltage here and a lower voltage there by 9.3 volts. That causes the transistor to turn off. So has anything new happened here? Not really. Instead of going to 0 volts and turning off the relay, it goes to minus 9.3 volts and turns off the transistor. But anyway, that turns that off. So what's going to happen? That's going to be staying at 0 volts because it can't move because that's locked at 0.7 volts because of the nature of the transistor. But then that voltage is going to climb up and up and up. At the same time, this is minus 9.3 volts. Let's put this back to being a capacitor again. And before, when this was 0 volts, it climbed up from 0 volts to 10 volts. Well, here, instead of going from 0 volts to 10 volts, it's going to go from minus 9.3 up to some other voltage. So what's it going to do? That voltage is going to go up. So this is charging just like before. The current is going this direction. That's charging. It starts at minus 9.3 volts and the voltage just rises. Negative voltage is not the opposite of positive voltage. It's just lower. So we went lower voltage. It's going to take a little longer to charge up, but it's going to charge up. It's going to hit 0 volts. It's going to keep on charging until what? Gets to 0.7 volts, at which point it's going to turn this transistor on. So what's going to happen? This, of course, had gotten up to 10 volts plus 0.7 and 10 volts. This transistor was off. Let's break the circuit there just to remind us of what's happening there. That transistor is off, so this went up to 10 volts, but this is forced to 0.7 volts by that transistor. This voltage just got up to 0.7 volts, so it turns this one on, pulls this voltage down to 0. But what's happening here? We had 9.3 volts across there, positive to negative. So when this was pulled down from 10 to 0, it pulled this one down from 0.7 to minus 9.3 volts. If you're not following that, go back to what we did here to show how that's just acting like a battery. Let's put it back there again. 9.3 volts, positive side to 0. So this is 0 volts. This is a lower voltage. If you have a lower voltage than 0, it's a negative voltage. There's our minus 9.3. Turns off that transistor, and we just go through the cycle back and forth again, just like before. So if we make our Astable multivibrator with bipolar junction transistors, we get this reverse voltage on the base. Does it change the way it works? Nope, still works exactly the same way, but it's interesting that we do get that negative voltage, but other people explaining Astable multivibrators will bring that up, so I just want to make sure you understand why we get those negative voltages there. But otherwise, the circuit works just the same. And if we replace these transistors with field effect transistors, I won't deal with polarity at this point. Well, they have such a high impedance that we're back to working just like we did before. We don't have that interesting anomaly of this voltage being pulled down to 0.7 volts. We don't get that same disparity, and it's going to act exactly like it did with the relays again. So only if we use bipolar junction transistors do we get that negative voltage on the base of the transistor. So don't get confused about that. Oh yeah, Astable multivibrator, we get negative voltages at the gates of the transistors, not with FETs. That was all because of the nature of the base to emitter junction of the bipolar junction transistor. And, well, while I'm at it, just for accuracy and explanations here, one other little anomaly that's worth mentioning. And that is when this goes to minus 9.3 volts, we do not get minus 9.3 volts at the base of that transistor because the base to emitter junction acts like a Zener diode. So what does that do? A Zener diode, well, when it's forward biased, it acts just like any other diode. So we expect to get 0.7 volts across it with the current flowing that way, positive to negative. But if we reverse the voltage, I'm going to make this into a Zener diode by putting the little tails on there. I'll redraw it. So make this into a Zener diode. Now, if we try to push the current that way, a normal diode just says, oh no, you're not either. But a Zener diode at a particular voltage, it'll start letting the current go, and it will change its internal resistance, if you will, to whatever it takes to keep that voltage constant. And so the base to emitter junction of a bipolar junction transistor acts like a Zener diode, and they typically have a breakdown voltage of around 5.3, 5.3, 5.6, somewhere around 5.5 volts. So when this tries to go down to minus 9.3 volts, putting this positive to negative like that, it can't, because this acts like a Zener diode and holds that to maybe about minus 5.5 volts. So instead of us getting minus 9.3 with this particular arrangement of voltages, it actually gets down to minus 5.5 because of the Zener diode-like action of the base to emitter junction of the transistor. So there, finally, is how a Astable multivibrator made with bipolar junction transistors works, and why does it get that negative voltage? Doesn't really make the circuit act any differently other than the engineering aspects of choosing the components, but it is interesting that with the bipolar junction transistors you will get that negative voltage on the bases. So there you have it. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.